Okay. All right. Hello, everyone. I'm Alan Hunter at Michigan Center for Materials Characterization, and we are going to be covering basic operation of the Helios. We're going to mainly cover SEM operation, and if we have time towards the end of the session, we will cover some of the FIB basics. But my expectation is that the FIB will be covered in a later training session. Please feel free to ask questions in the comment field. Hey, Jeremy, thank you for saying hello. And let's just get started here. Okay, so first thing I'm going to do is I'm going to do a brief overview of the system. And I'm going to move the camera a little bit here so we can see. Oh, maybe not. Well, I can't move the camera any more than this, so anyway, so this is our GoPro view of the side of the microscope. So this is the Helios system. I wish I could move the camera around to the other side, but the main components of the Helios are the vacuum chamber, which is the main large square object here. And then there are two different columns attached to this microscope. This is what we refer to as a dual beam system. So it has both an electron column, which is the vertical column here, and it has an ion beam column, which is on the backside over here on a 52-degree offset angle. So when we have samples in this chamber, we can image them with the SEM microscope, or we can image them with the FIB microscope, depending on what we want to do. Some of the other accessories that are on this tool, on the front here, this is the OmniProbe manipulator. We use this frequently for doing lift-outs, mainly making TEM samples or atom probe samples. We can also use this for doing probing work, or simply just moving things around. I've used it frequently if there's a dust particle or something right where I need to work. You can go in and poke it free with the OmniProbe. So these are not specifically used for lift-outs. Other accessories on this tool. On the front here, this device is called the NavCam. We'll go over this a little bit later, but it's useful for taking pictures of your sample, optical pictures of your sample for navigating. Especially if you have a lot of different samples in this microscope, this is a very useful accessory. Let's see if I can move a little bit here. I really can't move this. Okay. On the back side of the system, there is an EBSD camera and an EDS detector. So the EBSD camera is used for mapping out orientations of grains in your sample. It's used by a lot of researchers for metals analysis, oxides, semiconductor, thing like that, where you want to know the orientation. We can do preparation of samples in the microscope with the FIB and then do direct EBSD imaging. We can also do what's referred to as TKD imaging on the Helios, which stands for transmission Kikuchi diffraction. That's very useful for high-resolution diffraction studies, similar to what you can do in the TEM. There is also an EDS detector for doing chemical analysis on this system that allows us to map out elements in your sample with spatial resolutions of around 100 nanometers or worse. So very useful analytical capabilities. There's a variety of detectors on this microscope that we're going to go over today for imaging with the SEM. Just to name them all, we have the Everhart-Thornley detector, the through lens detector, and the ICE detector are all used for secondary electron imaging. There is a backscatter detector called the CBS detector, or concentric backscatter detector. And there is also a retractable stem detector on this microscope. So if you have a thin sample and if it's mounted in a special holder, you can do 30 kV stem imaging on the Helios, which is sometimes useful for biological samples or polymers, where you can get a little bit more contrast at low voltage compared to a TEM. So what we're going to do now is we're going to switch over to the user interface of the microscope. And I'm going to show you some of the different features of the UI. Now, the user interface of an FEI system is divided up into three main areas that I refer to. The first big area is your viewing area in the center. And right now I have it divided into quadrant view or quad view. And each one of these quadrants is going to show us a different imaging signal from the microscope. And these are configurable. So we can set them up to all show SEM images. We can set them up to show the FIB images. In the view that you're seeing right now, the top left quad is showing an electron beam image. The top right is the FIB image. The bottom right is the in-chamber CCD camera. And the bottom left is the NavCam image of a sample on the stage. Across the top of this screen is what we refer to as the toolbar. The toolbar has a variety of shortcut buttons in it that are useful for changing settings on the microscope. For example, if I want to change my accelerating voltage, I can click in the high voltage area and I get a drop-down menu of preset voltages that I can simply select and change voltage. Similarly, I can change my beam current by clicking in the beam current area, or I can also click in the magnification and get some preset magnifications. There are also buttons to access alignment windows. For example, this one is called Direct Adjustments, which opens up an alignment window. We'll use this frequently as we go through the imaging portion of this demonstration, and so on. So each one of these symbols does a different function. If you hover the mouse over them, it will show you what the symbol is called. For example, this one is the beam blanker. If you want to really know what all of these functions do, I'm not going to cover all of them today. It would take too long, but I would recommend that you look at the user manual for the system. You can access it on the tool by going to the Help dropdown and choosing Documentation, and this will bring up a PDF version of the user manual. Another useful area to look at is the Keyboard Shortcuts page, which will show you all of the various mouse and keyboard shortcuts that you can use on this system. I'll try to mention some of them as I go, but this is a good list to keep handy when you're just starting out with this microscope. The third main area of the user interface is the panel. The panel is over on the right-hand side of the screen, and the panel is subdivided into tabs. Each tab has a different name. For example, we're in the first tab called Beam Control. The second tab is called Navigation, and as you click through these panel tabs, you will see there's different functions underneath each tab. It will take a little bit of practice to remember where all the functions are that you want to control, but you're going to be moving through these tabs frequently. So the first tab is called Beam Control, and this is the main area for changing settings on either the electron beam or the focused ion beam. So you have another area to control accelerating voltage and beam current. You have a magnification slider. You can do scan rotation. You can control beam shift and astigmatism or stigmator adjustment, stage bias control, and then brightness and contrast. Now I should mention that the Helios software has multiple ways to change parameters. So as you've seen already, there is an area to change high voltage here. There is also, you can change the high voltage in the drop down up here in the top left. And you can actually change high voltage by clicking on the data bars as well. So if I go in the data bar and click where it says HV, this also gives you access to change high voltage. So it's going to be up to you to decide how you want to change some of these settings in the user interface, but it is very flexible. The second tab is the navigation tab, and this is where we directly control the coordinates for the stage. So when we're moving the stage around to go to different samples, we're going to type in the coordinates in these 5 boxes. The stage on the Helios will accommodate a 6-inch diameter wafer. So it's a fairly large stage. It has a vertical adjustment range of 10 millimeters. And as you'll see when we load samples, this range is very important, that you don't load samples that are too tall or too short. You will get into trouble that way. It can tilt between -10 degrees and +60 degrees, which is useful for working with the FIB. And it can rotate 360 degrees in a continuous circle. So very flexible for moving around, very, very nice for taking large samples. One of our other microscopes in the lab, the Nova NanoLab, can only accommodate a 2-inch diameter circular sample, so that this stage is considerably larger than the other systems in our facility. Third tab in the panel is the patterning tab. This is mainly used for working with the FIB, for doing FIB cuts or depositions. The fourth tab is called processing. This has the measurements and annotations feature. So if you want to measure the dimension of something, you can do that in this tab. It also has a very crude version of like a Photoshop application. So if you need to adjust the brightness or contrast or gamma levels, or add false colorization to your image, you can do that here. I generally do that in offline software. I don't normally do this on the microscope, but you can do that while you're recording the images if you choose to. And that's all down here in the bottom of this tab. The fifth tab in the panel is called the Detector tab. And this is where we're going to change detectors for our imaging. So when we click here, you can see a list of all the various detectors. The Everhart Thornley detector is ETD. The through lens detector is TLD. The ICE detector stands for ion conversion and electron detector. The ICE detector is mainly designed to work with the FIB, but it can also be used to image with the SEM. The CBS detector is the backscatter detector, concentric backscatter, and then STEM2 is the retractable STEM detector. External is just an external port, so if you had a custom detector that you wanted to put into the microscope, you could plug it into this terminal, and then you can actually image with it, but we don't do that very often. The sixth tab here is called sample prep. I almost never use this tab. This tab is a combination of features from other tabs, so it combines the pattern application area from the patterning tab with the navigation controls and scan rotation from the navigation tab and the beam control tab. I think the idea here is that when you're making a TEM sample or working with the FIB, that you can stay within this single tab and not move around. I don't find it very troublesome to just click through the other tabs, but I think that's the idea with the sample prep tab. So there's nothing in this tab that's not duplicated elsewhere. And then the last tab is called the alignments tab. As a user of our facility, there's really nothing in the alignments that you're going to need to worry about. Most of the alignments are locked out of the basic login anyway, but some of these alignments are in here. I would prefer that you don't mess with any of these. Come ask for help if you think there's something wrong with the Helios. So just kind of stay away from this last tab. When you come in to use the Helios, it's generally going to be pumped to high vacuum. And the first task that you're going to have to do is to vent the microscope chamber so you can load your sample. So when we walk in, we're going to go first to the beam control tab, and we're going to confirm our vacuum status. So down at the very bottom here, I can see this little colored icon is bright green. That tells me that the entire microscope is at high vacuum. If one of these areas of this little icon is orange or gray, it means that there is a problem with the vacuum in that specific area of the chamber. Especially if the two column icons, so the little vertical rectangle and the rectangle going on an angle here, if those are orange or gray, there's a problem and you need to come ask for help from staff. The chamber part of this icon will turn orange and gray as we vent it to load samples and then pump it down. We can get a reading of the actual chamber pressure right here. The unit is changeable. Right now it's in torr. Typically this will be in the mid 1 to the -6 kind of range for torr after the system's been pumping for a while. It's reading 1 × 10 to the -5 right now because we just vented and pumped it back down a few minutes ago. But after about 45 minutes, this should be down to maybe 5 × 10 to the -6 or so. If the vacuum levels are much higher, it could indicate that there's a leak in the chamber somewhere. So it's just something to pay attention to. Another thing I would like you to look at when you go to load samples is to look at the CCD camera. So this image here in the bottom right quadrant is a live view of what's inside the chamber. And we want to make sure before we vent the microscope that there's no sample close to the bottom of the SEM lens. So I can see this is the sample adapter. This will hold on to our individual samples here. And I can see that there's a lot of empty space between the bottom of the lens and the top of the stage adapter. The reason we need to check this is that this stage adapter is attached to the door. So when we open the door to load a sample, this will slide over to the right. And if we had a tall sample up here near the lens, it could potentially be dragged across the bottom of the lens and damage the microscope. And that is a very, very expensive problem, so we want to avoid that. Replacing the lens on this tool is probably $30,000 or so. So we need to be really, really careful about this component of the system. So I've confirmed that I know my vacuum is okay. I know I don't have any sample near the lens. So now what I'm going to do is vent the chamber. So I'm going to go to the beam control tab, and I'm going to look at the top here in the vacuum area. There's a button for pump, and there's a button for vent, and I simply click vent. And the system is going to ask me to confirm that I want to vent the chamber. And it says it'll take approximately 3 minutes, and we say yes. Now, this will actually vent quicker than 3 minutes. The 3 minutes is just sort of a default message, but the second that we can open the door, we can go ahead and load a sample into the microscope. You don't have to wait the full 3 minutes. Now, once I hit vent, you see down here that the vacuum status icon has changed to orange for the chamber. This means that the chamber is changing condition. So it'll stay orange until the venting cycle is complete, and then it'll turn gray. So that's normal. But again, you can see the 2 column icons are both staying green, which means that we're not venting the electron column or the FIB column. So once this is done venting, we're going to go over and load samples. So I'm going to switch the view back to the camera in the corner of the room, and we'll set this up so that we can look at the loading process. Let's see, what is that? Yep, that view looks pretty good. Okay, so when you hear the gas start hissing out of the gap around the door on this microscope, that tells you that the chamber is vented. So what we can do is go ahead and carefully grab onto the handle on the bottom of the door and slowly pull the door open. Now, this door does not open very far. This is the limit of the door travel. And depending on where the stage is, it can be rather awkward to reach in there and load samples into the system. So what we can do to make our life a little easier, and I apologize for the noise, the venting gas noise will stop here in a second. What we can do is move the stage to the extreme corner of its travel, which will make it much, much easier to access the stage adapter. So the way we do that is we go back to the user interface. We're going to go to the navigation tab, and I'm going to type in coordinates for X and Y to move it to the limit of its travel. Now this stage can go to 75 millimeters in the positive or negative direction for X and Y. So if I want to go to the limit of travel, I'm going to do 75X, and I'm going to do positive 75Y. I'm going to leave the other 3 values alone, and I'm going to say go to. And that will cause the stage to move out to the front. So now you can see that the stage adapter is in the opening of the chamber door, and I can reach it much, much easier. I'm just going to wait a second here for that venting gas to stop. Now, one thing that's very, very important, here you can see me kind of in the background. We always want to have clean gloves on our hands before we load or unload a sample. Contamination of the microscope is a huge problem in our facility, and the main way to prevent that is by always putting on a clean pair of gloves whenever you're going to load or unload a sample. Now, I'm currently wearing these gloves because of the coronavirus restrictions, and I've had them on for quite a while. So the surfaces of these gloves are actually rather dirty. So what I'm going to do is I'm going to put on a second pair of gloves over these. This would not be our normal operating procedure. Normally I wouldn't wear gloves at all until I had to load or unload a sample. So we keep gloves in the lab on the counter. That's always by the microscope. They're in all the different sizes. So if I grab a box of gloves and get a new pair, and hopefully that noise will stop here in another second. There it goes. Okay, so the venting cycle has timed out. Much quieter now. So I put on a new pair of gloves, and now I can go ahead and safely touch the inside of the microscope. Now you can touch the outside of the microscope without gloves, but just don't touch anything inside this vacuum chamber without clean gloves on. So the stage is attached to the door, which I mentioned already. So as we open the door, the whole stage comes out, and then the stage adapters screw into the rotation plate of the stage. So this particular adapter is used very frequently on the Helios. This adapter can hold 5 different small samples, but we can change these out. So I'm going to remove this adapter. It's removed by loosening the locking cone nut at the base by grasp it and turn it counterclockwise a few turns. And then the top of the adapter is removed by just turning it counterclockwise. It's a rather long screw, so you may have to turn it quite a few times. And I'm sorry, my hand's probably in the way, but I just want to stabilize it so it doesn't fall into the chamber. Okay, so this is the sample adapter that I was talking about. And if you see on the top here, it has positions for 5 small SEM stubs. So the stubs can go in these holes on the top. Once the samples are in the adapter, we then use the 1.5 millimeter hex wrench to tighten the set screws that are on the perimeter of the holder, and that is going to secure the samples in place. The center hole has a set screw right here. Some of the other adapters that we have in the lab are stored in the storage case on the desk. So if I rotate this camera a little bit to look over here. So the desk on the back here, there is a metal and glass storage cabinet that houses the other adapters. So feel free to open this up and use any of these other adapters. So some of the other parts that you'll find in here are, let's see if I can make sure I'm centered on this image here. So this adapter holds a single stub. This is useful if you have to do very high tilting, or if you're using the EBSD camera, you might want to use this. It has the same design as the adapter I showed you, so it's a single bolt that screws into the stage, and then it has a locking cone nut that it's used to secure it after you adjust the height. We have other adapters. This one is used for doing 3-dimensional EBSD cutting. So it has angles on the top that are specifically designed to help you do serial section cutting while working with the EBSD camera. So this is a rather specialized adapter. Come ask for help if you want to use this. This adapter is for doing STEM imaging. So this works in combination with a holder called the Toolbar and is used for holding TEM grids. And the grids get held horizontally on this adapter, and then the retractable STEM detector can insert underneath your sample and allows you to image in STEM mode. So this is required if you want to do STEM imaging on this tool. Again, this is a little bit more advanced topic, so come ask for help if you want to try using this. But I'm just trying to show you what's here. The last adapter that I want to mention is called the Universal Mounting Base. And it's this large kind of blocky thing of aluminum. This is an adapter kit that some people find useful and some people don't find very useful. This is installed onto the stage in place of any other stage adapter, and it's used for holding on to SEM samples and also TEM samples. Jeremy is asking, is there a sample holder for preparing FIB lift-out TEM samples? So that's a good question. We do have holders in the lab for holding the TEM grids. I mentioned the Toolbar holder. That is the FEI's solution. But what I generally do on the microscopes is use my own small TEM grid holders. You can buy them from companies like Ted Pella or EMS. There's a variety of designs out there. I have a couple very nice ones in the lab that you can borrow. So this particular one is made by OmniProbe, and it's a little clamping, I don't know if that's going to show up, but it's a little clamping holder for holding TEM grids, and it just fits into one of the holes like a conventional SEM stub. So I use holders like this quite a bit. Hopefully, if you have more questions about how we're going to attach samples to the stage, hopefully that'll become more clear as we go through the process. Now, the universal mounting base, the reason I want to just spend a few minutes on this is because it's not intuitive how to install this or remove it. So if you come in to use the system and there's no one around to help, you need to know at least how to take it out or put it back in. Now, it's actually, someone's taken this out and not put it away properly because the base is attached. So I'm going to remove the base first. Okay, so generally, the universal mounting base is in two parts. There's a spacer ring, which has 3 screws in it, and they're captured screws so they won't fall out. And then there's the universal mounting base itself, which also has 3 captured screws on the bottom. There should be a larger wrench in the lab. It's a 2.5 millimeter hex wrench. You need this to install or remove the universal mounting base. The way this part goes in is first, let's see if I can tilt this a little bit. You first put in the spacer ring. It sets on top of the rotation plate, and you'll see when you're looking down over the stage, there's 3 threaded holes that match up with those 3 bolts. So you're gonna put the 3 screws down into those 3 holes. Get all 3 screws started before you tighten any of them. And when you tighten these, don't over tighten anything. You want them just snug, but it's very possible to strip out those screws because they're all fairly small. Once the spacer ring's in, then the universal mounting base top piece goes in next. Now this one, to get at the 3 screws, you have to take the wrench and go down through these holes that are drilled in the top of the UMB. So it's a little awkward the first couple times you do it because the screw heads are not directly beneath these holes. So you have to tilt the wrench a little bit to the sides to find the screw heads. But hopefully this is more obvious when you're looking at it. So this just sets onto the spacer ring, and then you put the wrench down through the top, find the screw head, and tighten each screw. So there's 3 screws. Again, don't tighten one until you get all, I have it backwards. This goes this way. Get all 3 screws started before you tighten one. So 1, 1, 2, 3. Okay, so that's the installation procedure for the universal mounting base. Now, again, some people don't like this very much because it's kind of awkward to use, but if you choose to use it, by all means, feel free to put it in and take it out when you're done with your session. Now, to actually hold on to samples, there are a variety of little adapters over in the storage box that we want to get. So one of the adapters, which is this part here, holds SEM stubs. So you take your SEM stubs and they go into one of these 3 triangle shaped parts. And then there's set screws on the side for tightening them down. So you put your SEM stubs into this, and then this component drops into the universal mounting base track. Just like that. And then there's a clamping piece that has to go in next to the universal mounting base insert. And that is then tightened with the small set screw to wedge everything in place. So this component holds SEM stubs. The other component is the row bar. Let's see if you can hopefully see this. This is what FEI calls the row bar. This can hold 6 TEM grids at a time if you want to. I mean, you don't have to put 6 in, but it can hold up to 6. So the TEM grids are loaded into this. And then this is held by the second insert, which is this kind of a square insert with the 8 holes in it. It has a track milled down the center that you take the row bar and just slide it in there from the side. Make sure it's all the way down. And then this whole insert drops into the universal mounting base. And just like the SEM insert, you have a clamping piece that has to set in next to it. And then you use the small wrench, tighten that set screw, and that locks everything in place. I don't really want to use the universal mounting base kit today. I just wanted to show you kind of the basics of how it works. So I'm going to remove it, and we're going to do the rest of our operation today using this stage adapter. So we'll do that in reverse. I'm going to take the universal mounting base parts out. I'll put them back in the storage box. And then to remove the universal mounting base, I'm going to use the 2.5 millimeter wrench. And I'm going to first loosen the 3 screws in the top piece. And set that aside. And then I'll remove the spacer ring. Again, 3 screws. And set that aside. Now all of these components need to stay clean, so we want to store them in the metal storage box over on the desk. That just helps keep dust and things off of it. So I'm going to go put these away. I'll set those in there. Close the cabinet. And let's get back to loading samples for real now. So we're going to take our 5-position stage adapter, the cross adapter, and we're going to screw this into the center hole on the stage rotation plate. So just get that started. All right. Now, I don't want to lock it down just yet because I need to be able to reposition the height after I put the samples on the stage adapter. So let me see if I can get this camera a little closer. Maybe we can see a little bit better. I apologize here. I don't think this viewing angle is perfect for what I'm trying to show. Okay, so the couple samples that I have today for training are all on small stubs. I store them in these little disposable plastic tubes. It helps keep them all clean. But you can store your samples however you want. I do suggest, though, that however you store your samples, make sure it's a clean environment and make sure it's dust-free. So don't store your samples in cardboard boxes. Don't store them in paper envelopes. Don't wrap them up in tissue paper because the fibers from all of those types of containers will contaminate your samples, and the fibers can cause really, really horrible problems in the microscope. If a fiber goes up a column, it can actually wreck the entire SEM column. So make sure whatever you're using to store is clean, fiber-free. Plastic containers work well as long as it's clean. So I would avoid plastic bags. They usually transfer some oily residue to your samples. But usually hard plastic like this is okay. You can always wipe it out with some alcohol or something if you're not sure if it's clean or not. But take care with your sample storage. I should also mention we always use clean gloves when we load and unload samples in the microscope because we don't want to get the inside of the chamber dirty. But you should also always use clean gloves and tools when you're handling your samples back in your lab. So if I am working on this sample somewhere else and I'm touching it with my bare hands, I'm coating this sample with all kinds of oily residue, and then it doesn't really make a difference when I come over to the MC squared to use our facility because my sample is caked in oil. So wearing gloves after that is not going to help much. You're going to have all kinds of contamination problems. So just try to keep your samples as clean as possible. Now I'm going to use, I have these little small stub tweezers. These are really nice for small SEM stubs because you can grab onto the little groove on the outside and just pull them loose. So just pull them out. This sample, this is a filament from a light bulb. Just kind of a fun little sample to look at. So I'm just going to drop that down into the hole on the stage adapter. And next sample we'll put in, this is a piece of a silicon wafer, it's an Intel 65 nanometer processor that I tore apart a few years ago. So if we get to the FIB cuts, maybe we'll cut into this and look at it. We can see some transistors and gates and things like that. So I'll go ahead and put that in one of these positions. And then the third sample I'm putting in today is the electrode from a automotive spark plug. So just out of a regular old gas engine car spark plug. So these spark plugs, after you run them and they get used up, they form a lot of cool little nanostructures, which I think are neat to image. So we'll go ahead and put that in the third spot. And that set screw is a little tight, so it's not dropping down into place. So let's just loosen that. There we go. Now, anytime you're loading more than one sample, you want to take care that all the samples are at about the same height on their top. Hopefully, is this actually visible in the camera? It's not terribly clear, I guess. Hopefully you can take my word for it. But this sample right here is about 1 millimeter taller than the other two. And I want to make sure the top part of all the samples is in the same plane. Now, a millimeter height difference is not really a huge concern on the Helios, but what you don't want is to have a sample that's 1 centimeter taller than its neighbor. That's really, really dangerous. We're generally going to be working a few millimeters away from the bottom of the lens. So if you have tall samples that stick up relative to their neighbors, it's very likely you're going to crash into the lens when you're moving around. So I mentioned a while ago that this microscope can take a full 6-inch silicon wafer, but the caveat is that the entire sample has to be the same height. So a big flat wafer meets that criteria, but when you have multiple samples like this, try to get them all in the same plane. Now the way we can do that is I can't shorten the tall sample, but what I can do is raise the short samples up a little bit. So I'm going to tighten the set screw to hold that tall sample in place. And I'm going to go over to the other samples. These are the shorter ones. And I'm just going to raise them up a little bit before I tighten the set screw. You'll find that most of these SEM stubs are longer than they need to. so they allow you to do this type of procedure. Wow, my hand is right in the way. Sorry. Yeah, this is not a good view. So, all right. So now I have, I've raised up the 2 short samples, and they are now approximately the same height as the 3rd sample. So now we should be much safer when we go to move around inside the microscope. Now the next part of this procedure is extremely important. So I hope you pay careful attention to this. We need to set the height of this adapter, right? I haven't locked it down yet. I can turn the whole adapter clockwise or counterclockwise to either make it shorter or taller. The way that we measure the height is by using this gauge that should be sitting next to the microscope. So this little block of aluminum is set onto the flat part of the stage, and we want to look at where is the top of our samples in relationship to this bottom this surface right here. This surface right here. Now, hopefully you can see there's writing on this. And the 2 things written on it is there's a line that says max, and there's another line that says 4. Those 2 lines refer to specific heights of your sample, and it tells you what working distance you can reach if you raise the stage to its maximum height. It's a little bit of a confusing way to do this, but this stage has 10 millimeters of vertical travel. It's more likely that you're going to load your sample and it's going to be too short. So if you want to work at 4 millimeters working distance, which I should back up. Working distance is the distance between the top of your sample and the bottom of the SEM lens. And 4 millimeters is the standard height on this microscope. So if you want to be able to get your sample to a 4 millimeter working distance, you have to be even with the 4 line or taller than it. So remember, 10 millimeter stage travel. So if you put your sample exactly at the 4 line, you're actually starting 14 millimeters away from the lens. So 14 millimeters away, you bring the stage up 10 millimeters in vertical, and then you end up at 4 millimeters. So make sure your samples are always taller than the 4 millimeter line. The max line does not refer to maximum height. It refers to maximum SEM resolution, which on this microscope is a 1 millimeter working distance. So if you want to be able to put your sample at a 1 millimeter working distance, it has to be even or taller than the max surface, which is the bottom of this nose. The top part of this gauge does not mean anything. It's completely meaningless. Your samples can actually be taller than this whole device and still be safely inserted. However, I don't have a way to show you how tall a sample can be before it runs into the lens. So be very careful. This gauge does not tell you your samples are too tall. It tells you your samples are too short. That being said, the safest way to load samples in the Helios is to set up your sample so it's just barely above the reference line that you care about. Now for today's demonstration, I want to show you high resolution SEM imaging, so I want to be able to get to 1 millimeter working distance. So what I want to make sure is that all 3 of my samples are barely above the max line. So the way I do that is I'm just going to set the gauge on the stage, and I just kind of sweep it over the side of the sample, and the gauge should not go over the sample, but just barely. And right now my samples are about 2 millimeters above that point. So what I want to do is I'm going to turn the whole stage adapter clockwise a few times, which will make it shorter, and then I'll try again. So this is just about perfect. The corner of the height gauge is just barely touching the aluminum stub. So all my samples are above the max line, but just by just a half a millimeter or so. Now if I overdo it here, if I go a lot shorter. Now the height gauge will clear over top of all of my samples. So I would avoid this condition because you can run into trouble. If your samples are too short, you won't be able to get to the working distance you want to work at. Which, especially if you're using the FIB, that's a real big problem. So again, my recommendation is set up your samples so that this gauge just barely catches on the side of the aluminum stub or on the side of your sample if your sample is really tall. Obviously don't smash this into your sample and wreck your sample, but so right now this is just about perfect, and hopefully this is showing up in your view that the samples are just slightly taller than the bottom of that gauge. So I have a question here from Sakun that he says, is 4 millimeter eucentric height? Yes, the 4 millimeter condition is the eucentric height on the Helios. And I think we'll cover that when we get the samples loaded. So I've used the height gauge. I've determined that this is an appropriate height. So now what I'm going to do is I'm going to lock the cone nut. So I just hold the top piece so it doesn't spin, turn the cone nut clockwise until I feel a little bit of resistance against the stage, and that everything is secure. It's a really good idea, after you think it's locked down, just give a little wiggle to the top, make sure it's secure. If you don't get the cone nut fully tightened, and this wobbles around like this, you won't be able to do high resolution imaging because your samples will vibrate and move around a lot. So make sure that that's tight, otherwise you'll have problems. So now our samples are loaded onto the stage adapter, and the next process is we're going to use this component on the door called the NavCam to take a picture of the stage. This is extremely useful when you have multiple samples on the Helios. So to use the NavCam, let me see if I can pick up this. I'm stuck. Okay. So the NavCam is mounted here on the top of the door, and to use it, after your samples are loaded and locked down, you then just simply swing out the camera until it stops, and the samples will automatically move beneath this camera lens. Now in the user interface, let me go back and switch real quick. In the bottom left quadrant, you should see a live image appear with the NavCam, and it will automatically adjust the exposure until the software is happy with the light balance. So once you see the exposure looks good, then we want to record that picture. So that's still a live image. You can see if I put my hand under it, that's still live. The way to capture the NavCam image, let me go back to this view. There is a button on the NavCam housing right here. There's a button. So once everything in the NavCam image looks good, you then just simply press down on that button and let go, and that will start the process of acquiring the NavCam image. Now the whole process takes a few seconds. If you're looking at the user interface, you'll see the image go black, and then it'll acquire the image with a little progress bar. When the whole process is complete, you see the light on the NavCam turned off. That tells you that it's done. So now what we do is we're going to swing the camera back closed. And the stage moves back to its original position. This stage uses piezo motors to move in the X, Y, and rotation axes. Piezo motors are rather loud when they move at high speed like that, so that kind of horrible noise is normal for the Helios. You won't hear that when the door is closed. All right, so now what we're going to do is we're going to carefully close the door and pump the system down. Now I'm going to go back to the user interface view, because when you close the door, I want you to be in the habit of looking at the CCD chamber camera. So in this camera view here, let's make this full screen so you can see better. As I close the door, I want to make sure that my samples are not going to run into the bottom of the SEM lens. And this is really the only view to see if you're going to hit it. Again, that height gauge doesn't tell you if your samples are too tall. So this is really the only way to check. So as I'm watching the live CCD camera view, I'm going to carefully push the door closed. And I'm going to make sure that I have clearance between the sample top and the bottom of the lens. And everything looks good right now, so I'll just keep pushing the door closed until it stops. When you're manipulating the door, try not to slam it closed. That's not a good thing for the microscope. You can actually shake some things loose on the stage and cause some alignment problems. Okay, so the door is closed, and then to turn on the vacuum pump, we're going to take the mouse, go to the beam control tab, and then we can either hit the pump button, or we can also use the built-in plasma cleaner. So if you notice, there's a little down arrow next to pump. You have the option to pump or pump with sample cleaning. So if I choose pump with sample cleaning, it'll run the plasma cleaner for 5 minutes. That's attached to the chamber, which will clean the chamber and also cleans your sample. And then it will continue pumping down. So the pump with sample cleaning will take probably about 8 minutes to run that cycle. And then you can image directly and hopefully your samples are clean. If we just choose the pump button, it'll just directly pump the chamber down. It takes a couple minutes. And that's what I'm going to do today. So we're just going to hit pump, and that'll turn on the vacuum pump. It's a good idea to gently push on the chamber door for a few seconds when you turn on the pump, just to make sure the door seals. If the door's open, the roughing pump will just run for a minute or two and then give up. And then the chamber will sit at air pressure for all day. So now the system's pumping. And we can see here in the user interface down in the bottom right, the chamber icon is again orange, which means it's changing condition. So that will turn green after we reach high vacuum, and that's when we can start imaging with the SEM. So I know I spent a lot of time on sample loading. The reason for that is that most of the mistakes people make on these microscopes involves either the loading or unloading process of the sample. Either they load their sample too short or too tall, or they forget to tighten a screw and their sample's loose. And those tend to cause the most trouble with these microscopes. So once you get your sample loaded, you know, you're 90% of the way to a good image, I think. So for now, we just have a minute or two while we're waiting for the high vacuum to be reached, and then we can start imaging with the SEM. Okay. So when we start operating the microscope, what I'm going to do is I'm going to have this window up showing the manual user interface, or the MUI, the MUI. The manual user interface is one way to control parameters like brightness and contrast, astigmator, magnification, X and Y beam shift, and coarse and fine focus. There are also mouse shortcuts for doing all of these and keyboard shortcuts. I'm going to try very hard not to use the mouse shortcuts today, but if I do, I apologize. So Jeremy is asking, how long does it normally take to pump and plasma clean? So it's about 8 minutes for that whole process. So what it will do is it will partially pump the chamber down, and then it'll run the plasma cleaner for the fixed amount of time, which we have it set to run for 5 minutes. And then it will finish pumping the chamber down to high vacuum. So the 5 minutes is in addition to the normal pump down time, which on the Helios, it's normally about 3 minutes. Gabriella is asking, what is the yellow line on the bottom right screen indicating? The yellow line. Oh, this 4mm line, I think, is what you're asking. So it's just a reference marker to show you where 4mm working distance is on the CCD camera. It's useful because sometimes it's hard to tell where where your sample is in relationship to the lens, because this isn't really a calibrated image. So the 4mm line is approximately at that working distance. Now, one thing I should warn you is that in the EMAL login that we're using right now, the 4mm line is locked, and it's always going to be right here. If we leave the Helios logged in under the service login and someone double clicks on this window, it will move the 4mm line around. So don't blindly assume that this 4mm line is right, because it can be mistakenly moved if we don't leave the tool in a good condition. So if you think your sample's 4mm away because you focused on it and linked your working distance and did all the procedures correctly and it's not matching this marker, don't worry about it, because the marker's probably in the wrong spot then. But as long as we stay logged in under the normal login for the users, this should be fine. So what I've noticed here is that the chamber pressure is now reading a value. So the vacuum gauge doesn't turn on until the turbo pump has reached, I think it's 75% of its maximum speed. So once the chamber vacuum gauge is on, you can get an idea of your vacuum levels. So it's currently 1.5 times 10 to the minus 4. I don't remember offhand, but I believe it's somewhere around 8 times 10 to the minus 5 is the vacuum you need to get in order for this to turn green. One of the reasons why the vacuum is rather high right now is because I had the chamber door open for so long. The longer you have the door open, the more moisture and gas and things like that go in there and stick on the surfaces of the microscope. And all of those molecules, they take a while to pump out. So best practices when we're not doing training is to open the door, load your sample, close the door, turn on the pump. You don't want to leave the door open for an hour if you can help it, because it makes the chamber take a lot longer to pump down. So unfortunately, we just have to wait for another minute or so here for the chamber pressure. All right, so I believe we're almost there. So we're 9 times 10 to the minus 5. Again, I think it's like 7 or 8 times 10 to the minus 5 is where the chamber will turn green in this icon, and then it'll let us turn on the SEM. So just while we're waiting here, let's make the CCD camera full screen again. So in this image, you can see some of the components that are attached to the roof of the microscope. Normally when I do in-person training on these systems, I like to point out everything that's hanging inside the chamber, but that's not really easy to do today. But the large central cone in this view is the SEM objective lens. And it's actually one of 2 objective lenses on this microscope. So the Helios SEM has a low resolution objective lens and a high resolution objective lens. And the part that you see here is the high resolution lens. Now in the software, it's rather confusing, but they refer to the two lenses as the high resolution lens and the ultra high resolution lens. This is just FEI being FEI, I think. But I generally refer to them as either like the standard lens and the high resolution lens. They're also referred to as the mode 1 and mode 2 lenses. It kind of depends on what part of the software you're looking at or who you're talking to or what user manual you're reading. So be aware that there's two independent objective lenses on this microscope. One for lower resolution wide field of view imaging, one for high resolution imaging. This cone shaped object over here to the right of the CCD camera is the objective lens for the focused ion beam column. So the gallium ions come down this column on an angle and they intersect the SEM image view right here at the 4 millimeter working distance. So if our sample is in the appropriate spot, then the SEM and the FIB are both looking at the same feature. The other thing that you can see in this image is this sort of a wire cone up here in the top left. This is the collection grid for the Everhart Thornley detector. So that style detector uses a phosphor-coated scintillator, and this grid is biased and it pulls electrons from your sample, or secondary electrons from your sample up into this detector, and then they strike the scintillator and they generate light, and that is then turned into an imaging signal through a series of amplifiers. So that's what this thing hanging down right here. There's actually, it's hard to see when it's not moving, but there's an object right here in the front. This is the detector and collimator for the EDS detector, so that's for doing chemical analysis. So sometimes this is retracted and then you won't see it, but this sort of arc-shaped thing right here is actually the EDS detector. You can't really see anything else in this view, but again, when you're here using the tool in person, if you would like, come ask for help and I will point out all the rest of the components that are up on the roof of this microscope, because there's quite a few things inside the vacuum chamber that I think are neat to look at. Okay, so our vacuum is now suitable for turning on the SEM. You can see the chamber has turned green. So what we're going to do is let's go back to quadrant view. And let me turn on the MUI view. Okay. Now, here's first shortcut key that I just used is F5. So F5 on the keyboard is going to switch you between full screen view and quadrant view on the user interface. Full screen view is very helpful if you're only using the SEM. It keeps you from having to squint into the corners of the user interface. So feel free to switch that as much as you want. When you're using the microscope in person, you'll actually find that there's a second monitor in the room. We're not showing that right now because of the limitations of our live streaming, but you can project one of these quadrants onto a full screen image on the second monitor. So you can actually have 5 different images available. So you can have the 4 quadrants in the user interface like I have now, and then you can have one of these duplicated on the monitor to the side, full screen as well. And the way to turn that one on and off is Control and F5. Now, if you forget keyboard shortcuts, you can find them again by looking at the keyboard shortcuts PDF. So if I open that up, you can see there's a whole bunch of keyboard shortcuts in here. Hopefully this is showing this window. Yeah, it's showing. So, you know, you can look in there. You can also find most of the keyboard shortcuts in these drop-down menus up at the top. So if I go to the window drop-down and I scroll down here and I can see large image window and it tells me the shortcut is Control plus F5. Or if I want to switch between single and quad image mode, the keyboard shortcut is F5. So keyboard shortcuts are great if you really like them. There's probably about 100 keyboard shortcuts on the Helios, so I don't know all of them. I don't use most of them, but F5 is one that's worth remembering. And you can look around up here. There's other keyboard shortcuts. In the scan menu, there's quite a few of them. that you can try. So we're in the quad view, and what we want to do now is we want to turn on just the SEM. And the way we do that is we go to beam control in the panel, and we're looking for this beam on button right here. Now you have to be careful. In the FEI software, these functions apply to the selected quadrant in the user interface. Now hopefully you can see, let me turn off the MUI. You can see that one of my quadrants has a blue data bar and the other three have gray data bars. The blue data bar tells you what is the active quadrant. So whatever microscope image is being projected to this quadrant, that microscope will be controlled by this panel right now. The way that you can tell what microscope source image is showing is by the icon in the bottom left corner. There are 4 different icons. If you click on them here, you can see there's an electron beam symbol, which looks kind of like a little nuclear electron cloud kind of thing. The ion beam symbol is the just jumble of blue and yellow. I guess they're supposed to be like parts of the atom, but like protons and neutrons or something. But that's the symbol for the ion beam. The CCD camera is the light bulb symbol. And then the NavCam is the compass. And you can see I can change these by just clicking in the symbol on the bottom left of the quadrant. So if I want to change the parameters for the ion beam, I just click on quadrant 2 because that's set to be an ion beam image right now. So then if I click beam on, I will turn on the FIB. Or if I change the accelerating voltage or the beam current, that applies to the focused ion beam. If I want to change conditions for the SEM, I take the mouse and I click once on a different quadrant. For example, quadrant 1, which is an electron beam image, and I know that based on the symbol in the bottom left. And now anything I change in the panel on the right-hand side applies to the SEM. Now these functions also apply to the manual user interface. So if I'm going to take my hand and change the magnification knob or adjust the stigmators or beam shift or any of these apply to the selected quadrant. It's something I see troublesome for new users is they will accidentally select the FIB quad and they'll change magnification or change focus and they think it's applying to the SEM and then they don't see the result they're expecting to see. So try to be in the habit of deliberately selecting the quadrants before you make changes to the system. And when you're working with in the dual beam mode with both SEM and FIB at the same time, you have to train yourself to constantly be selecting the quadrants based on which beam you want to change or which condition you want to change. So again, we're going to click on the SEM quadrant, and then we're going to go over here and click beam on. When you click beam on, you should hear a little clicky noise in the room. That is the column isolation valve opening up. That separates the column from the chamber, and you may hear the aperture motors move a little bit. The way to know that your electron beam is actually on is by looking at the color of this button. So a yellow button means that your SEM is turned on and is available to image. If I click on it again accidentally, the button still says beam on, but it will go back to being gray in color. So gray means you don't have a beam. Yellow means you do have a beam. And this is another one that new users have trouble with sometimes, is that they double click on the icon because they're used to Windows double clicking or something like that. And then they go and they start imaging and they have just a black screen and they can't figure out why they have no image. It's because they turn the beam on and then off again. So make sure you just look at that. Yellow is on, and it takes a second for it to show up. So now I have a beam, but I'm not live imaging because my scanning is paused. To start and stop the scanning, you can use this little pause toolbar button up here. This says Start Image Acquisition. There's also keyboard shortcuts for this. So if you go to the Scan menu, the start and stop, it's F6, starts and stops scanning. So if you like keyboard shortcuts, go for that too. Unfortunately, in this version of FEI software, these indicators in the corners of the quadrants are not clickable buttons. So as much as I want them to be, you can't click on this to start and stop scanning. In the newer versions of the software, like on our Helios plasma FIB down the hall, this is a selectable button, and you can click on that to start scanning. But on this, the Helios 650, this is just an indicator, it's not a button. So if we hit pause, we now have a live image. You can see we're scanning. We can change our scan speeds by changing the dwell time with this selector in the toolbar. So the right arrow will make you scan faster. The left arrow makes it scan slower. Or you can click in the middle and directly go to one of the available scan speeds. So if I want to go, say, to 30 microseconds, I can. The time here refers to the amount of time the beam spends on every pixel in the image. So faster times will result in faster image refresh times. So if you're going to be moving around a lot or doing a lot of focusing, I would recommend you use one of the shorter times, maybe 50, 100 nanoseconds, something like that. But you'll get a feel for this as you use the tool. Other parameters you can change are the resolution of the image. So the default resolution on the Helios that most people will use is 1536 pixels by 1024 pixels. So this is the X and Y dimension. If you want to improve the scanning speeds, you can go to lower pixel count, which will cause the image to refresh quicker, but you're sacrificing pixels in your image. You can also go to much higher pixel count. So it'll go up to 6,144 by 4096. This will slow down your scanning quite a bit, so I generally don't recommend you do this if you're doing live imaging, but feel free to use different numbers of pixels for acquiring images. But I like the 1536 by 1024. I think it's a nice size. Now, just like I mentioned, that all the parameters apply to the active quad. So if I click on the FIB, then all of these parameters up in the toolbar now apply to the FIB microscope. So again, make sure you know which quadrant is selected, because there's independent controls for the FIB and the SEM. So the first thing we want to do is just make sure we have an image. What I would recommend you do is just take the magnification knob, turn it counterclockwise several times. There's no stop on the knob, but that'll make sure that you're at the lowest magnification on the system. Right now it shows that we're at 74x magnification. If you start out at the high magnification, which right now it goes up to like 3 point something million, obviously you don't really see anything. So I recommend start off with a relatively low mag. Now there's no sample below the SEM right now, which we can tell in the CCD camera image. But at the lowest magnification, you should be able to see the inside of the SEM lens, which is this big circular feature right here. So if you can't see that at the lowest magnification, it tells you that there's something else wrong with your imaging. Maybe your brightness and contrast are not correct. So maybe the last user left the brightness and contrast turned way down, in which case you want to adjust your brightness and contrast to try to find an image. If you prefer, there is an auto contrast brightness button in the toolbar, so you can select that and the software will try to adjust contrast and brightness for you. Sometimes it does a good job, sometimes it doesn't, so I would use this with care. But what it is very useful for is getting you close in terms of brightness and contrast level. Some people, it takes them a while to get the image adjusted, so feel free to use that. So we have an image here. Other parameters to look at if you're having trouble getting a starting point is look at your voltage and look at your beam current. If the last user left it at a very, very high voltage or a very, very low voltage, or maybe a really ridiculously high beam current, or very, very low beam currents, you might have trouble getting an image. So just make sure that your starting conditions are reasonable. I'm going to recommend that you use 2 kV and 100 picoamps anytime you don't know what you're expecting. So for me, 2 kV and 100 picoamps is my default imaging condition on the Helios. I use these conditions for probably 75% of my imaging on this tool. So I recommend that's a good starting point. But feel free, if you like more beam current, you can go to higher beam currents. If you want more resolution, you can go to smaller beam currents. Those are easily selectable. So for example, if I want to go to a little bit higher, I can just pick 1.6 nanoamps, and the tool will increase the beam current up to that higher value. So you see with the higher beam current, we have less noise in our image for the same scan speed. Keep in mind, though, you sacrifice resolution by going to high beam current, and you also potentially will charge up insulating samples. So, be careful about that. Your choice of accelerating voltage is, I'm going to leave that up to you, but my recommendation on the Helios is try to stay below 5 kV. This tool will go all the way up to 30,000 volts if you want to use that high of an accelerating voltage. But the Helios is a very modern high-resolution SEM, and it really is designed to work the best between about 500 volts and maybe 3 kV. So if you're getting outside of that voltage range, you're really using the tool in a condition that it's not really optimized. If you're doing all your imaging at 10 or 20 kV on the SEM, you would probably be just as well served by using the TestScan Mira 3 or the Nova NanoLab, and you'll have easier access on those tools because of our scheduling. So really what I'd prefer to see is I want to see students using the lower voltages on the Helios, because it's where this tool is really, really well designed for. That being said, use whatever conditions that you want to. You are in full control of your experiment, and I'm not going to be looking over your shoulder, but again, it does make me a little sad when I see images at 20 kV on the Helios. So again, low voltage, 2 kV, 100 picoamps is a great starting point, and you shouldn't have too much trouble. Other parameters to look at if you're having trouble getting an image is look at your detector and look at the detector mode. So of all the various detectors, I would recommend you start off with the Everhart Thornley detector, the ETD detector, and it should be in secondary electron mode. If the last user was working with backscatter mode, you may find that you have a very odd image or maybe no image at all, depending on the setup. So the detector and the detector mode can be switched in the detector panel. So you choose ETD detector, and then I would use secondary electron mode when you're starting out. And you can also change these in the data bar. So by just selecting detector, ETD, and then you can change the mode, secondary electron mode. So we have an image. What we want to do now is to move around and go find a sample, because we don't want to just sit here and stare at vacuum. The best way to move on the Helios is to use the NavCam. We are, let me move this window out of the way for the MUI. So we have this NavCam image taken of the stage, and to use it, you just take the mouse and double click on a feature that you want to go to. So to start out, let's go to the spark plug sample, which is this one right here. I'm just going to double click on the center of it, and that will cause the stage to move to that position. Now the alignment of the NavCam relative to the stage is not exactly perfect. So if you click on a feature on this image, you might not end up right on top of that feature, but hopefully it's close enough that you can figure out where to go. For example, if I click like this corner of this stage adapter right here, let's see how far off it is today. It's not too bad. So this is the actual corner of the stage adapter, and it's off by maybe a millimeter. Usually the offset is predictable, so if you can figure out what the offset is, it should generally apply to the whole NavCam image. So now that I know that I need to click a little bit lower than a feature, if I want to go find this little white dot on my sample, I just need to click a little bit below it, and that should take me right to that spot, which is right here. Close enough. If you need more resolution on the NavCam image, you can select it. So click on quad 3 to select it. Go to the image processing tab, and there's a digital zoom function. So you can digitally zoom in on feature, and then you can drag this image around a little bit to reposition it. So this is really useful if you have small features that you're trying to find. Again, the software thinks that I'm looking at this part of the sample stub, but in my SEM, I'm actually looking right here. So there's a little bit of an offset there. So just keep that in mind. The NavCam, when you zoom in on this, it'll actually show you your approximate field of view. So as I change my magnification, you can see that little box kind of changes size. It's trying to show you what you're looking at on the screen. You can actually click on that and drag it around. So if I just click and drag this like over here and let go, it'll actually move the stage over to that spot. You can also just click and draw a box on top of a feature like that. And then stage will move to that spot and zoom in to fill that field of view. So it's just kind of useful navigation tools. Again, you want the image, you want to make sure that you know what the offset is between the NavCam and the actual stage position. So this is a spark plug electrode, and what we're going to see when we zoom in on it and get our image optimized is that there's a whole bunch of little platinum nanoparticles and carbon nanoparticles on it. It's a pretty easy sample, I think, to image, and it's mildly scientifically interesting. I guess if you're not into looking at nanoparticles, it's not going to be exciting to you, but it's what we're going to use as a start here. Once you find your sample that you want to look at, the next process is to determine how far away this surface is from the lens. So in my CCD camera, I don't really know how far away the sample is from the bottom of the lens. I want to position it to be 4 millimeters away, but I have to measure this gap first before I can move. The way that we can measure distance from a lens to the sample is by focusing the image. So let me turn on the MUI panel display, and I'm just going to leave the MUI up in the bottom left for now because we don't really need the NavCam anymore now that we found our sample. So I'm going to turn up the magnification a little bit. I recommend you use at least 2000x for this. You can focus at low magnification, but it's tricky. It's very easy to do it incorrectly. So give yourself a better chance of doing this right. I always suggest 2000x as a minimum. And then what we're going to do is just turn our focus knob. So we have a coarse focus and fine focus. They both do the same thing, and just one adjusts faster than the other. So I'm going to turn the coarse focus knob one way and then the other, and I'm looking for the image to come into focus. Now, as I'm changing focus, you should hopefully notice this parameter right here in the data bar called working distance. That number is changing. So as I change focus, I'm changing the distance that the SEM is focusing away from the lens. So when my image on the screen is in focus, that number represents a good way to measure the distance to the sample. However, if the sample is not in focus, then that number is meaningless. So let's get our image back in focus again, and we can use the fine knob or the coarse knob. Feel free to spin these knobs as fast as you want. You won't damage them. I see new users, sometimes they'd be very, 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 very cautious with these knobs, and it just takes them forever to get a good image. So, take your finger and just spin these things like crazy, because we don't want to waste a bunch of time trying to find focus. You won't hurt the microscope. There's no physical stops in any of these functions. So once we have found our focus, then we need to tell the microscope that, yes, my image is in focus. Please use this value as our reference. And the way we do that is this icon up here in the toolbar with the red question mark. It's called link sample Z to working distance. And what that's going to do is it's going to assign this number to the Z-axis of my stage. And to show you what I mean, let's go look at the navigation tab right now. So for my Z-axis, it says we're currently at 0.0 millimeters, which means the stage is at its lowest height possible, and the positive direction is up. So if I were to type in a number, say if I type in 1 and hit go 2, the stage just goes up 1 millimeter. this coordinate system is not terribly useful for us for microscopy. Now, if I know the distance between the lens and the sample, this working distance, and then I click this red question mark, it's going to transfer this 9.9 millimeter value over here to the z-axis, and then that will now become our z-axis coordinate system. So we're going to do that. I'm going to click this. It's no longer a red question mark. Now it's a green up and down arrow. And then the 9.9 millimeter value is now showing for my z coordinate. And the other big change is the positive direction for the z-axis is now down. So now our z-axis is not referencing the raw height of the stage, it's referencing the working distance between the lens and the sample. So now if I were to type in a small value like 1 millimeter and say go 2, that's going to cause the stage to go up so that the sample ends up 1 millimeter away from the bottom of the lens. So be very, very careful that you know which way the positive direction is on the z-axis before you move it, because 0 millimeters will cause a collision if you're linked, and 0 millimeters will move your sample away from the lens if you're not linked. So I'm going to hit escape to abort what I was doing because I don't want to move to 1 millimeter just yet. Where we do want to go is to 4 millimeters. So again, to summarize, I find my sample, I focus on the surface at higher than 2000x magnification. I click the link button in the toolbar, and then I can go over here to the Z coordinate and I can type in 4, and I can hit the enter key on the keyboard, or I can select go to, and that will then raise the sample up so it should be 4 millimeters away from the lens. Now the calibration of that measurement is not perfect, especially when you're making really big changes in height. And the software is going to remind you of this by changing that little link icon to a red circle. So this little red circle appearance is the software trying to tell you that you should focus and link a second time. So what I usually do is just zoom in a little bit higher magnification. Let's make sure we're still in focus. Pretty good. And we'll just click this again. And I think I'm exactly at 4 millimeters, basically 3.998 millimeters. If I focus and link a second time, I see I'm actually at 3.9941. So a little bit off. Depending on what your accelerating voltage is in your working distance when you do the first link, I've seen the error be as bad as like 2 millimeters. So sometimes you can be off by a lot. But if you want to be exactly at 4, you generally want to do this twice. So focus, link, move to 4 millimeters, focus, relink, move to 4 millimeters again. And now I have very high confidence that we're right at 4 millimeters. And you should see that the 4 millimeter reference line in the camera lines up with the top of the sample. Now to move around, I think I skipped over this. I need to go back a step. To move around with the SEM image, so the couple ways to do it. The first way is just double click. So if I take the mouse and I double click on a feature, that feature will move to the center of the screen. And this will change with magnification. So if I go to low mag and I want to go to a different spot, I can just double click on that feature and it will move to the center. Another way to move is I can take the mouse and click and drag a box on the screen and then let go of the mouse, and the stage will move to the center of the box, and it'll also adjust the magnification for you. So let's say I want to zoom in on this, this platinum ball up here. I can just kind of highlight and draw a box around it, and the stage will zoom over to that spot and also change the magnification to zoom in on it. If I want to go to lower magnification, you click on the lower right corner of the box first, and then drag up and left, and you see there's a little minus symbol next to that magnifying lens in the box. That'll cause you to go to lower magnification. So you can kind of zoom in and out with the mouse by drawing boxes around features and zoom in and out on them. Or you can double click on features, which moves them to center. Another way to move is by pressing down on the wheel. So I have my mouse center wheel here. If I press down and hold this, so click it down, the mouse becomes a joystick. So if I click and hold the wheel down and then move the mouse in some direction, the stage will start moving in that direction. I can change the speed by moving that yellow arrow closer to the dot, which makes you go very slow, or I can move the arrow very far away from the dot, which makes you go fast. And you don't have to let go of the button. You can just move all around in different directions. This is probably the fastest way to move around the stage if you're not using the NavCam, because if you go to the lowest magnification on the screen and then move around like this, you can move very, very fast to go between different samples. But again, I generally prefer to just use the NavCam. It's the easiest way to get from one side of the stage to the other. Other ways to move are you have the arrow keys on the keyboard. So if I kind of move this for a second, well, hopefully you understand, right? You got the up, down, left, and right arrows on the keyboard. If you push one of those, for example, I'm going to push the left key. The stage moves by about one field of view in that direction every time you push it. So I can move left, and I can move up, or I can move right. And this will change with magnification. So if I'm at lower magnification, it'll move by a larger step every time I push an arrow. I don't use this feature very much, but sometimes it's nice if your sample surface is contaminating under the beam, because you can get everything focused and lined up, and then you can just slide right a couple fields of view and take your picture, and hopefully it doesn't contaminate. The arrow keys don't work very well if you push them a whole bunch of times. It generally only moves like once or twice, and sometimes you get some stuttering effects on the stage. It also doesn't like it if you hold the arrow keys down. So if I just hold the arrow key down, it'll start moving in a rather chaotic fashion. It's kind of hard to predict how far it's going to actually move. So I recommend if you use the arrow keys is just push the arrow key, let it move, push the arrow key, let it move. Other ways to move around on the stage is you can use the coordinates in the navigation tab. So right now we're looking at actual coordinates. So if I know where I want to go, I can say, like, let's go to 0x, and that will move me to this particular coordinate. If I want to go back, I can double click on last position and it'll take me backwards one motion. You can also change this to relative, and then I can do relative moves based on my current location. So if I do a relative delta x of 1 millimeter, then I can slide around 1 millimeter at a time, or I can do -1 and go backwards. If you find a stage location that you want to save, like say this feature is very important to me and I want to find it again, I can click add in the save position list, and now this shows up as position 1. I can single click on it twice slowly, and then I can change the name. So I can say spark plug, and I can rename it. So now if I go to some other, let me go some other location, and I say I want to come back to that, I can just double click on that spot and it'll take me right back. And because the X and Y axes are piezo motors, they're very, very precise. You should be able to go back to save positions within half a micron or so precision. So it's very, very, very nice when you got to move around big distances. Let's see, I think those are all the main ways to move around. There's some other neat features buried in here that use, you can actually use images that you acquired to go back to those spots where you took the image, but I think that's a little bit advanced. But you can do that. You can read about it in the help guide if you want to try that. So let's say for now, this is the spot we want to be at. So our next step is to determine our imaging conditions that we want to look at and to optimize the SEM for imaging. So we already talked about changing the accelerating voltage and changing the beam current. So again, you can change those with these drop-down menus. Keep in mind that for the accelerating voltage, this drop-down menu is a preset list. You are not limited to these specific voltages. If you want a different voltage, like say I don't want 2, I want 2500 volts, you can go to the beam control tab, and here where it says high voltage, you can type in any arbitrary voltage that you want to image at, and the software will take you there. The limit is 350 volts is the low end and 30,000 volts at the high end. So you have to stay within those constraints, but don't feel that you're limited by these preset values. The beam currents, you are limited. These are the only available beam currents on the tool, so they remove in discrete values. I think there's like 20 of them or so. For general imaging, I would stick in the maybe like the 25 picoamps to maybe 0.2 or 0.4 nanoamp range. So just kind of stay kind of in the middle of the list here, and you should have good success. The big beam currents are used for mainly analytical purposes for either EDS or EBSD. And then the smallest beam currents are going to be used for very high resolution imaging. So we'll just sit here at my default recommendation and we'll see how well we do. So 2 kV, 100 picoamps. To optimize your image, you want to check the column alignment. And the column alignment is accessed by going to this button in the toolbar called Direct Adjustments. So if I click Direct Adjustments, it opens up a little window that is floating. I can move this around and park it wherever I want, which is useful if I'm going to be changing conditions a lot. And let's go to full screen here. I'll go to so I hit F5. We'll go to full screen mode. The main adjustments that we're going to look at are called source tilt and lens alignment. The source tilt alignment is a set of deflectors that changes the angle the electron beam comes down the column from the electron gun. We want the beam coming straight down through all the lenses in the column, which will give us our brightest signal and our best resolution. Now for TEMs, there's another alignment coupled with this called source shift, but we don't do source shift on a routine user alignment on the Helios. We just do source tilt. I align the source shifts about every 2 or 3 weeks on the Helios, and they're usually pretty stable. So if you think that there's an alignment problem on the microscope, come talk to me, and we can look at realigning the source shift if you need it. But usually source shift is not a big issue on this tool. It's mainly source tilt. The second alignment is called lens alignment. Lens alignment is going to modify the path of the beam so that it passes through the center of the objective lens. And the way that we find the center of the lens is by using a lens modulator. The Helios actually has 2 modulators available. There's a lens modulator, which modulates the strength of the lens current, or there's a high voltage modulator, which wobbles your accelerating voltage. You do find slightly different alignment points depending on which one you use. For the TEM users, this is hopefully familiar to you. The current center alignment versus like anode wobbler or voltage wobbler, things like that. The software is going to recommend one or the other. If you're lower than 5 kV accelerating voltage, you should use the HV modulator, and if you're at 5 kV or higher, you should use the lens modulator. Really, you don't have to worry about it. This button is always going to show you the recommended alignment modulator. So right now I'm at 2 kV, so it says HV modulator. If I were to close this window and change my voltage up to 8 kV, and now if I open up direct adjustments, you see that it shows me lens modulator, and if I click the little down arrow, it says this is the recommended one because I'm higher than 5 kV. So let's go back to 2 kV. Now what you have to be careful of is if you have this direct adjustment window open, this button won't change until you close it again, but it does change the which one is recommended. So HV modulator is the recommended modulator for 2 kV. Okay, so I'm getting a little bit, I guess, too much description here. We should keep moving forward. The way we do source tilt is we're going to activate a scanning mode called crossover. So this button is right here. We turn on the crossover mode. Crossover mode will cause the scanning of the microscope to shift from the sample surface, and instead it scans above the aperture in the column. So by scanning the beam above the apertures in the column, we see a bright spot when the beam is passing down the center of the column. So this image is still formed by the electron beam causing secondary electron emission from the sample, but it only occurs in this disk where the beam is able to pass down the column. So all the other black space in this image is where the electron beam is just hitting the sides of the column or the top surface of an aperture or something like that. The center of this image has been calibrated by FEI to designate the optic axis of the microscope. So what we want is we want the center of this bright spot to line up with the center of this image. And the way we adjust that is by grabbing the source tilt adjuster and simply moving this around. So if I drag this way off to the corner like this is really, really terrible alignment because the bright spot does not match with the center of the image. So it hopefully will never be this bad, but it could be if the alignments are really terrible on the Helios. But normally you don't have to make such a big adjustment. So we drag the source tilt adjuster around so that the bright spot is centered on the yellow crosshair. The yellow crosshair just marks the image center, and that's all we have to do with the source tilt alignment. Now you may notice here there's a very faint spot in the corner. If I turn up my contrast, you can see it better. This spot is another set of apertures that's used with the monochromator mode. If you see both spots, don't align to the small spot. Go with the big spot. This one, if you align to this, you will get very weird imaging behavior on the column. So also note, I'm adjusting my brightness and contrast to make this easier to see. Sometimes when you go to crossover mode, you can't see the spot. So just crank up the contrast and it'll show up eventually. So that's source tilt. There's also a zoom function here, so you can zoom in and out to make this easier to find the spot or not. Some of the different beam currents, this spot's bigger than others. So that's source tilt. We turn off the crossover mode. And now we're back to our regular imaging mode. After you do source tilt, then we're going to turn on the modulator for the lens, and we're looking for image motion. So right now, the image is going in and out of focus because it's modulating the accelerating voltage. Right now, the lens alignment's actually pretty good. You can see that there's a little bit of shaking in the image, but it's mainly going in and out around the center of the image. If I grab the lens alignment and I really mess this up, so let me drag the lens alignment like way off to the corner here. Now you can see that in addition to going in and out of focus, the image is shifting back and forth in this diagonal direction. And we want to get rid of that shifting. So we're going to use the lens alignment 2D adjuster to try to minimize the image shift. Now if I move the 2D adjuster left and right, it's going to add and subtract to the horizontal part of the wobbling. And if I move it up and down, it's going to add and subtract to the vertical part of the wobbling. So sometimes it's a good strategy to try to go after one direction of wobbling at a time. And you can do that by clicking on these line segments off to the sides. If you click on the dot in the center of the 2D adjuster, you can do both directions at the same time. So that looks pretty good, at least good enough for now, and I'm going to turn off the high voltage modulator. If you're trying to do very, very high resolution imaging, there's another set of modulators called stigmator centers. If you click on this second tab here, you've got another set of modulator X and a modulator Y. If you turn these on, what these do is it causes the stigmator adjuster to move back and forth either in the X or the Y direction. And this can cause some image shift as well. So here, let me drag this off to the corner and you can see. So if your stigmator centers are very, very bad, you'll get image shift as well with this alignment. And then you can fix that. I'm going to right click here and I'm going to say go back because it was pretty good. These have amplitude adjusters for the modulators if you need them. Right now we're doing fairly low resolution imaging, so these aren't really important. But again, for the highest resolution imaging, you want to align all of these to get the best image quality. So our column is now aligned, and this alignment is specific to my voltage and my beam current condition. And it's actually also specific to my working distance. So if I make a change to my accelerating voltage or I make a change to my beam current, what you should do is go back and redo your source tilt and redo your lens alignment because they will not be correct anymore. The Helios maintains a list of basic alignments for all these values, so hopefully you should find that it images pretty well even without doing these alignments, but again, for best image quality, you should check these every time. After we do our column alignment, our next process is going to be adjusting focus and astigmatism. So I'm going to go find a feature that's relatively small and easy to focus on. We'll just use this little surface right here. So I'm going to start off with focus. So I'm going to change my focus. And you can see I actually have a pretty decent image without doing anything for astigmatism. But as I go back and forth through focus, the image gets blurry and then gets sharper and then gets blurry again, which tells me where the best focus condition is. This takes some practice if you're not used to operating an SEM, but you'll hopefully get the hang of it very, very rapidly. Astigmatism is a little bit trickier to adjust. The best way to adjust astigmatism is to find some round, small features. And as you go back and forth in focus, those features ideally just become uniformly blurry. If you see them distort in any particular direction, it tells you that you have astigmatism in your beam. And I'm going to look around on this sample because somewhere around here there's a whole bunch of little small features that work really well for this demonstration. I just got to find them. Yeah, here's some. All right, so this surface is mainly platinum, and all these little specks here are little carbon nanoparticles deposited on the surface. So what I'm going to do is I'm going to turn on a mode called reduced area mode, which gives me this little tiny window, and I'm just going to kind of park it over top of some of these particles. And I'll slow my scanning speed down a click or two, and let's also adjust our brightness and contrast. All right, so if I adjust my focus, hopefully this is apparent, but if you can see that these little round nanoparticles in here are distorting along two different directions. So if I go one side of focus, they're all elongating along this direction. And if I go to the other side of focus, they now are elongating along this direction. So this tells me I have a little bit of astigmatism in my image. So what I want to do is try to find my best focus condition where these things are not elongating in either direction. And the best way I find to do that is just to wobble the focus back and forth a few times and try to figure out where that center transition point is, which I think it's right about here. So these particles are not elongating in either direction. Now I'm going to use my X and Y stigmator to try to improve the image quality. So I'm going to start with just the X knob. We'll go one way, it gets fuzzy. I'll go the other way, it gets better, and then fuzzy again, and go back. And try to make the image look as nice as I can. And then I'll use the Y knob, back and forth, and try to improve the image quality. After you do that, go back and repeat the process. So what you should be doing is doing focus, and then stigmator, stigmator, focus, stigmator, stigmator, until you're happy with your image quality. So I can do focus, stigmator, stigmator, and so on until you're happy with it. And hopefully we can see that our image quality is a little bit better now that we've optimized the column alignment as well as focus and astigmatism. So now we're ready to take a picture. So let's change our magnification. We can set up our field of view for whatever we want to see. Let's just go with this. We're at 1200x. I'm going to adjust my brightness and contrast a little bit. Now to record an image, you have several options on the Helios. The first option is to simply slow your scan speed down so that the image looks acceptable to you, and then hit the pause button. So if I hit the pause button, so if I hit pause once, the image will completely recycle, and then it will stop once the scanning gets to the bottom of the image. So now I have a frozen image on the screen, and I can simply go to File and choose Save or Save As, and save that image to wherever I want. If I am scanning and I hit the pause twice in a row, the scanning stops immediately. So if you have, say, I'm changing my contrast and brightness like this, that'll leave a scan line in the middle of the image. So one pause, it will always finish the current image and then stop. Hit pause twice, it stops immediately. And then if I hit pause again, it restarts my scanning. So that's the first way to get an image. Just simply hit the pause button and save it. The second way is called the snapshot. The snapshot tool is one of two preset image acquisitions. So there's snapshot and then there's a photo tool. Both of these do the same thing. It's just you can have different dwell times and different resolutions assigned to each one. There is actually a shortcut key for snapshot. It's F4 on the keyboard. For some reason, it never shows up in the user interface, but F4 is your snapshot shortcut. F2 is the photo shortcut. So if I hit F4, that activates the snapshot, which right now is doing a 3 microsecond scan. It takes an image and then pauses. If I hit F2, F2 right now is doing a 20 microsecond scan, so it's a much slower scan, which gives me a little bit better image quality. While you're acquiring these images with the photo or snapshot, you can also hit the pause button twice if you want to abort the scan. That way, if you accidentally are taking an image that's going to take like 10 minutes, you can get out of it without having to wait. You can change those settings for either photo or snapshot by going to the scan dropdown and going to the Preferences tab. The shortcut for this is Control-O. And in here, in the Scanning tab, you have a list of dwell times. These are the dwell times that you have available for your live scanning speeds. So these speeds up here. And you can change those however you want. And then the two icons on the bottom with the cameras next to them are your snapshot preset and your photo preset. So if I want to change these values, say I don't want 3 microseconds, say I want 1 microsecond, I can type 1 US. Now my snapshot will do a 1 microsecond scan. I can do line integration. I can do frame by frame integration. You can change the resolution that it acquires in. There's an action function which will tell the software to either auto-save the image or to bring up the save window for you after you acquire the image. So this is nice sometimes, or you can just set it to be none. After you get everything done, you can hit apply and then say, okay, so now if I hit F4, I get a 1 microsecond scan dwell time instead of the 3 that was set there before. Let's see. Again, no big difference between the photo and snapshot. It's just they're just two sets of values that you can have, so you don't have to constantly remap those parameters. So let's say that we want higher resolution imaging than what I've showed you. Right now we're using the low resolution SEM lens, which is still pretty good for looking at features down to maybe a couple hundred nanometers in diameter. For example, if I zoom in right here and bring up my measurement tool, let's do a circle measurement. You know, I can see features around 100 nanometers, not too much trouble, but you know, these little small features in here don't show up very great. The way to use the high resolution lens is this icon up here in the toolbar. So if I hover over it, it says switch to SEM mode 2 immersion mode. I mentioned there's a bunch of different names for these lens modes. In this particular toolbar, mode 1 field free mode refers to the low resolution objective lens. That's the mode you start out in. Mode 2 immersion mode refers to the high resolution objective lens. And then mode 3 is a hybrid mode that uses both lenses at the same time, and it's used primarily for doing EDS analysis. It helps remove some of the X-ray background from your sample, from your spectra. For imaging purposes, mode 3 and mode 1 are very similar. So there's a couple very special cases where mode 3 works better, but for beginners on the Helios, I would recommend just use mode 1 or mode 2. So if I want to switch to mode 2, I just click mode 2, and it'll switch to the other objective lens. Now I need to warn everyone about this. The mode 2 lens is the lens that hangs down right here by the sample. It's an extremely powerful electromagnetic lens. If your samples are magnetic and you switch to that lens, you can potentially pull your sample right off the stage and it'll stick to the lens and damage the lens. So do not use the high resolution lens if you have a magnetic sample in the chamber. And I'm not talking permanent magnets, I'm talking iron samples, some nickel samples, cobalt, things like that, iron oxide particles, anything of that nature that will become magnetized if it's close to an electromagnet. though all those samples will cause you problems if you use the high resolution lens. Now, if you're lucky and your sample stays put on the stage, you will find that you have just terrible, terrible imaging conditions because the magnetic field of the sample will distort your lens field. Now, I don't have any magnetic samples in the chamber, so I'm going to go ahead and click this icon to go to, I clicked mode 3. I don't want to go to mode 3. I want to go to mode 2. Now, in addition to changing the objective lens, the other thing that changes on the tool is the detector will switch automatically to the through lens detector. The through lens detector is required to image with the high resolution lens, and you'll find that the software disables the other detectors that are not allowed. So I cannot use the ETD detector and I cannot use the ICE detector when I'm using the high resolution lens mode. Now, because the detector changed, you see I lost my image. It's probably just a brightness and contrast problem. And because I am using a different objective lens, you see my focus is a little bit off. And I'm going to have to open up my direct adjustments, and I'm going to have to redo source tilt and lens alignment to optimize my imaging. So let's go ahead and go through that again. When you get practice on the Helios, you should be able to do all the column alignments in just 20 or 30 seconds. So we'll start off with focus. Let's lower our brightness down a little bit. And let's zoom in now to some small features here. I like to use the reduced area window for doing this. Find it's useful. So check our focus. You can see we have a lot of astigmatism. And let's turn on the HV modulator. And you can see here we have some lens alignment problems that we need to sort out. So let's move the adjuster to the left, and I can see my problems are getting worse. So let's go to the right. All right, so now it's just wobbling in the vertical direction. So now I'm going to move the lens adjuster up and down, try to get rid of that wobble. That looks pretty good. We'll turn off the modulator. I'll double check my focus, and now you can see I have a lot of astigmatism. So again, I want to find that transition point where those round particles are not distorting in either direction, which I think is right about here. Then I'm going to go to my X and Y stigmators. I'll try to improve the quality of the image as best I can. And then I'll go back and repeat the process. So focus, stigmator, stigmator. That looks pretty good to me. So now, because I'm using the high resolution lens, I should be able to zoom in and you can see all these small particles are much, much clearer. So if I zoom in and take a look at some of these little guys now. Let's just pause our scanning here. And now if we measure, do I still have the measurement tool active? Yes, I do. Let's see, what's this? That's 30 nanometers. What are these little guys here? They're about 14, 15 nanometers in diameter. Generally, you can resolve features to about 3 to 5 nanometers in diameter with the Helios if you get your image conditions really perfect. Even though it has a resolution specification of 0.6 nanometers, you still need a feature to be a couple times larger than that value in order to actually see it. Let's look around. I know there's smaller stuff on this sample. Just to show. Now I see that it's 3 o'clock. I originally scheduled this to only run from 1 to 3. I guess we're going a little bit slower. I'm going to keep going with the training to just kind of get through some more of the SEM training. If some of you have to leave, I understand. This will be archived. You can watch it in later. All right, let's see here. This maybe some little stuff. Oop. You actually see there's a little bit of like image drift going on here. This is a problem we're trying to get resolved with FEI. This is not normal. for this instrument, but we're just gonna have to work around it for now. Let's see how big are these? Yeah, so now we're seeing these particles are maybe around 10 nanometers in diameter. And they still have pretty sharp edges. So hopefully you believe me that if I find stuff small enough, we should be able to see, you know, sub 10 nanometer diameter features with these conditions. Now, some of the neat things you can do with this microscope, and especially in the high resolution lens, is this lens mode can be used as an imaging filter to do backscatter imaging or secondary electron imaging. So let's say I want to know where the carbon is and where the platinum is on this sample. If I go to my lens mode, instead of using secondary electron mode, I use backscatter mode. The backscatter mode, once I get the focus back, should show me where the light elements are and where the heavy elements are. So for example, this stuff over here, this is carbon, which it's a little bit out of focus. There we go. So in a backscatter image, anything that appears bright is a higher atomic number, and anything that appears dark is lower atomic number. So you can see this mass of stuff is actually little platinum nanoparticles buried in carbon, and the carbon is sitting on the platinum surface. And this shows up really well with the backscatter mode of the TLD detector, the through lens detector. If I go back to secondary electron mode on this same feature, now you see that the mode change causes your focus to shift a little bit. Secondary electrons show you mainly topography. So in the secondary electron image, I can see that this feature is rather bumpy, but it's not immediately obvious that there's two different, vastly different atomic number materials in here. It just looks like kind of a bumpy mass of stuff. But again, there's actually platinum and carbon mixed in this that is easy to see when you use the backscatter detector. Some other neat things you can do with the TLD detector is you can use it to filter out charge buildup. So let's say you're imaging nanoparticles that are some kind of oxide material. Let's say, let me find a different spot here. This stuff. So this stuff kind of charges up, and let's make it really bad. Let me go up to a higher beam current. Let's go up to like 0.4 nanoamps. And I'm not going to align the column just for time's sake, but you can see that as I'm scanning over this stuff, it's charging up like crazy, which is all these little horizontal flares. What I can do is by changing the mode to custom mode, I can then, let me back up. Let me go back to secondary electron mode. The mode changes on this TLD detector change the value of the suction tube, which is an electrode that either collects or repels electrons from the detector. So when it's positively biased, it's attracting the low energy secondary electrons, which are also the electrons affected by this surface charge. If I move the suction tube down in bias, once I hit 0 volts and go negative, instead of attracting those low energy signal, I actually repel it. And the idea is that the backscatter electrons that are higher energy will still form the image, but the lower energy secondaries will not. So you can use this as sort of a filter mechanism. So as I turn this down, you see that some of that charge is leaving the image. So we just keep turning this negative and more negative until all the charge is gone. So something like that. And now we are able to image this part of the sample without charge. Now there's still a little bit of charge here, and I can deal with some of that by changing my scan speed. So faster scanning also helps in this situation. So now I have a relatively charge-free spot on my sample. Now the charge is still there, it's just not forming my image. Now if you want to take a picture like this, if I use my photo or snapshot settings, because I have those mapped to very slow scanning, I'm going to get a lot of charge buildup and my image looks terrible. So one of the ways around it for this type of situation is, instead of doing single slow scans, is use integration. So if I go to my scan preferences, I'm going to go to my snapshot preset. Let's set a dwell time of 100 nanoseconds and hit apply. So now if I hit F4, I get a snapshot, and I don't see, there's no charge here, but my image is very noisy. So what I want to do is I want to integrate a bunch of images together. So instead of doing a single 100 nanosecond scan, let's do 100 of them. And this software has the ability to do drift correction when you're doing integrated images. So I highly recommend you leave drift correction on. So now if I hit F4, I get an integrated image. And there's actually a little progress bar creeping along the bottom here. You can't see it because it's behind the movie picture, but when I have a integrated image with those same conditions, you can see it looks much better than the single slow scan did or the single fast scan. And if I were to actually modify my brightness and contrast a little bit better, we can actually see that there's features down in there. Now if I zoom in on this, you can see that some of the charge comes back. And it looks like I definitely have some astigmatism I should have fixed. And definitely some lens alignment problems as well. Now, hopefully you can see that these little particles look rather fuzzy on their borders. That's probably because I'm using such a high beam current that I'm getting above my resolution limit for this condition. So just kind of keep that in mind. Big beam currents mean less resolution. So pretty neat, I think. So let's go back to our regular imaging mode. So we have, again, secondary electron and backscatter mode, and then the custom mode are the three that I use a lot. Charge neutralizer mode just sets the suction tube to 0 volts. It's supposed to do what I just showed you with the custom mode, but the problem is you have to go negative with the suction tube in order to get it to work. So 0 doesn't really do anything. And then downhole visibility sets the suction tube to a very high positive voltage. And what this is for is if you want to image down in the bottom of small cavities. Let me find one. I can hopefully show you what this does. Yeah, this will work. So there's like a pit on the sample, and that pit acts as an electron trap. So if I want to see what's down in the bottom, I can raise my brightness and contrast way up. But you see that by doing that, so I can see the bottom of the pit, it causes the top surface to become saturated. It's way too bright. So what the downhole visibility mode is supposed to help with is to try to help get images from these pits without oversaturating the surface. So if I go to downhole visibility, this one doesn't always work great, but the idea is that it helps kind of pull signal out of the bottom so that you can see down in there without completely blowing out the top surface of the sample, which it looks like it's doing a pretty good job here. So that's the downhole visibility mode. So let's go back to secondary electron mode, and let's move on with some of the other aspects of SEM imaging I want to show you. So right now we're using 2 kV. Let's say we want to go down lower in voltage. Let's say we want to go down to 500 volts. And let's drop our beam current down. Let's go down to, say, 50 picoamps. So at low voltage, your image will be much more surface sensitive. So you'll be able to see a lot of detail on the surface. Like these small little nanoparticles and things will show up better. But at some point, you'll lose resolution because of the low voltage. So low voltage will cause mainly chromatic aberration problems, which we can avoid by using the monochromator. Now, the monochromator mode on the Helios has some restrictions to it. First off, it's called UC mode. So you see here in the direct adjustments, there's this UC centering. UC stands for unicolor, or FEI didn't want to call it monochromator, so they called it unicolor. It only is available at beam currents of 25 picoamps or less, and at voltages of 5 kV or less. So if I go right now, I'm at 500 volts, but 50 picoamps. If I look in my beam drop down, I can see I have UC on and UC auto available, but it won't let me turn on UC mode because my my voltage is too high. So if I drop my, or sorry, not my voltage, my beam current. So if I drop my beam current down to 25 picoamps, now UC will be available. So I can say, if I say UC auto, it'll just automatically turn on UC mode anytime I enter a condition where it's allowed, or I can force it on by say UC on. So now that UC is on, you see that UC centering becomes available in the adjuster, and the monochromator is activated. There is an additional alignment step for this mode. Here, let me drop, I'm gonna go down a little bit lower in beam current. Really, UC mode is best for really, really high resolution conditions. So we should be down in these low beam currents. When we go into the crossover mode, you'll notice that the crossover spot will look a little bit odd. It will have a series of bands in it. The UC centering is an extra alignment step that needs to be done. And what we do is we're gonna grab onto this adjuster and we're gonna just kind of move it up and down. And what we're looking for is to try to center that pattern of bands as best we can on the screen. The way to think of it is that there's like a virtual aperture right here that's blocking out part of this pattern. So as you move the UC up and down, you'll start to cut off parts of the spots. So just kind of put that, just kind of scan it up and down a little bit and position it roughly in the center. And then when we move left and right with UC centering, you'll see that you also kind of cut off the spot in each direction, and you want to try to just guess at the midpoint. Fortunately, this isn't terribly specific on how you do it, but just try to get that roughly centered as best you can. After you do UC centering, you then do source tilt, and you put the spot right in the center of the screen, just like we did before. And then we turn off crossover. So that's the extra alignment step for the UC mode. So now we're going to continue with our lens alignment. So we turn on our HV modulator. We can see we have a lens alignment problem. So we'll fix the lens alignment. So I move the lens alignment left and right and up and down, get rid of the wobbling. That's pretty good. And then let's zoom in and fix our focus. And astigmatism. And so now we should be able to get a pretty decent image, hopefully. If I slow my scan speed down, it's not too bad. I'm up at 80,000x, but we can see some relatively small features here. Let's try our focus one more time. I think I'm a little bit out of focus. Well, it looks like it's about as good as it's going to get right now. But for a 500 volt image, that's pretty good. If you try to image at 500 volts on one of the other instruments in our lab, you'll see that this is orders of magnitude better resolution than you're going to find on those tools. And hopefully we can still see features, you know, that are pretty small. Certainly sub 100 nanometer. So that's the UC mode. I know I went through that really fast, but hopefully you can you know, review the video again later. A lot of this stuff is covered in the user manual as well, so you can read about some of the specifics on these in more detail there. So again, UC mode, if you have it set to auto, then anytime you're at 25 picoamps or less and 5 kV or less, the UC mode will automatically turn on. If you don't have the auto mode selected, then you have the choice of whether you want the UC module turned on or off. So if I turn off the UC module, this is now the same beam condition, 500 volts and 6.3 picoamps, but without the monochromator turned on. So you can image with or without it. So another aspect of this that I want to show you is the backscatter detector. So let's hop back up to 2 kV and let's go to a little bit higher beam current. Let's go 0.2 nanoamps. All right, and I'm gonna hit F5, go back to quad view. Let's say we want a really nice image. I showed you the backscatter mode of the through lens detector, but the backscatter mode is not anywhere as good as the dedicated backscatter detector. So if we want to use that detector, we're going to go over here to the detector tab and we can select the CBS detector. And this is an insertable detector. So the software tells me the CBS detector is currently retracted. And then I can say insert, and that'll bring that detector in. I'm going to back up a step. You have to be extremely careful with this detector. And it inserts from the side above the sample, and you have to make sure that you have a 4 millimeter clearance between the lens and the sample over the entire stage. Otherwise, you risk having this detector hit something. Because it comes in from the side, if you have a tall sample sticking up over here, that detector will slam into it on its way in. And it comes in very fast. To show you what it looks like when it comes in, I can also insert it by clicking on the CCD camera and then going to detectors, and you see you have control over the CBS insert here. So if I say insert, it says please confirm, and I say yes. And that detector comes in very quickly. So unfortunately, the bottom surface of this is a very thin piece of silicon. That's the actual detector. If it hits anything, it will break. And it's about a $10,000 replacement if that happens. So you need to make sure you don't have anything sticking up above 4 millimeters anywhere in the chamber before you use this detector. What I prefer to do when I'm using the backscatter detector is to set up my quadrants so that I can image both secondary electrons and backscatter at the same time. So if I click on quad 2, which is a FIB image right now, change this to electron beam, and then change this detector to be CBS. Now I can image both signals at the same time. So if I hit pause, that will start this image scanning. Now the backscatter detector doesn't react very well to fast scanning speed. So I'm scanning at 100 nanoseconds, and you see my image is garbage. So what I need to do is I have to slow down my scan speeds. So as you slow down your scanning, the CBS detector will produce a much, much, much better signal. And this is why I really like to have the secondary electron image available, because you can use the secondary electron image for your focusing. And then once you get your image set up, you can take a nice slow scan with the CBS backscatter detector. So here, let's zoom in on some of this stuff. And hopefully you can tell that the signal and the dynamic range is just considerably better with this detector versus the backscatter mode. Which actually I can even do backscatter mode. So if I put the TLD detector into backscatter mode, and you can kind of see the difference here between these two detectors. The CBS is a lot better for backscatter imaging. Now the CBS detector has 4 ring segments on it. Each segment can be used to form a separate image. Let me get my focus a little bit better here because this is really bad. Again, I mentioned you should always do column alignment. I'm trying to avoid doing a lot of that right now just to show you the detectors, but if I was taking images for real, I would align the column every time. So this image right now is using all 4 of the ring segments of the CBS detector, which is really going to give you a lot of signal. You can also use different parts of the detector to use to see different components of the backscatter. So if I pick the A ring, which is the centermost ring of this detector, this is going to show me the most atomic contrast in my image and the least amount of topographic contrast. If I choose the outermost ring, the D ring, it's going to have the least atomic contrast in the image and the most topographic contrast. Now, the problem is that because of where my sample is, I'm actually not projecting a lot of backscatter electrons onto the D ring, so it doesn't even have any signal. So let me try the C ring, which is a little bit closer to the center, and we'll see. Yeah. So there's still some backscatter contrast here, but a lot more topography will show up in this image versus the elemental contrast. Now, if you want, you can have all these images up at the same time. So I could set all of my quadrants to be electron beam images and set this one to be CBS. So I could say I want my quad 4 to be my C ring, and I want quadrant 2 to be my A ring. And I could do the same thing with quadrant 1 and quadrant 3. And then you can acquire all these images simultaneously. So let's say I want to do that. If I just go up here and hit the photo button or the snapshot button, it will only record one quadrant. What you have to do is hold the shift key down on the keyboard. So if I hold shift and then hit F2 for photo or shift and F4 for snapshot, that will then record all active quadrants at the same time that are set to the SEM. So you see I'm getting a simultaneous scan on all 3 of these quadrants, which I can then save each quadrant as an image file if I want to. I'm going to stop this because I don't actually want to save any pictures today. Oop, cancel. So those are the basics of the backscatter detector. Whenever you're imaging with the backscatter detector, it will pause your CCD camera image. So if I go back to my CCD camera here, this is a frozen image. So be aware of that this will not give you live feedback of what's going on in the chamber. And the second, if I unpause my CCD camera image, it will stop the CBS image. So you cannot image with the CBS detector and have the CCD camera image live at the same time. I'm not going to go into it today with this because this is kind of basic training, but another imaging mode available for the SEM is called beam deceleration mode or stage bias. This is used if you want to get very, very low accelerating voltage imaging. I mentioned that 350 volts was the minimum voltage that you could go with the SEM. With stage bias, you can apply a potential to the sample that will slow down the electron beam even more as it approaches the surface. And with this mode turned on, you can get down to 50 volts landing energy if you choose to. It also improves your resolution quite a bit at the really low voltages. So if I wanted to image these nanoparticles at 500 volts and I wanted really spectacular quality, I would probably use the beam deceleration mode instead of trying to image it with the native 500 volt accelerating voltage, and that would most likely give me better image quality. Again, beam deceleration is probably a whole topic for a separate video. There's alignment and choosing parameters and things like that are a little bit complicated, but in terms of just using the mode, you just simply choose how much stage bias you want and you turn it on, and it turns on the beam deceleration mode. But again, I don't want to go into all the particulars of actually aligning this and setting it up. So I think I've covered most of the basics of SEM imaging with the Helios. What I'm going to do now is I'm going to spend maybe 10 or 15 minutes on just some FIB basics, because I know some of you guys want to see that. But again, we'll do a separate video that's going to be specific to the FIB. We'll probably make like a TEM sample or something during that training. So what I want to do is click on the CCD quad. I'm going to click retract, and we'll take out the CBS detector. Oh, I should mention the stem detector is insertable here as well. Don't ever insert the stem detector unless you have the specific stage adapter in for stem. This detector will slam into the bolt on this stage adapter because it's trying to come in below the sample, so it will cause a bad collision if you insert it with this stage adapter in. So just don't click the stem to insert. Okay, so for the FIB stuff, let's use the NavCam image, and let me move this MUI image out of the way. Let's go over to a different sample. Let me get my digital zoom off here. Let's go over to the semiconductor chip. So again, I can just double click and that will move me over. When you go to a new sample, what you want to do is first focus on that surface and update the link, because this sample might be a little bit different height. So when I zoom in on it here, I can focus, and this tells me that this sample is 4.2 millimeters away from the lens. But because my link was on the first sample, the software thinks it's still only 4 millimeters away. So all I do is simply click the link button a second time, and now the software is referencing this surface. So I can say go to the 4 millimeters, and I'm going to turn off the high resolution lens. You can use the high resolution lens with the FIB, but it's considerably easier to work in the field free mode. So now to use the FIB, here I got some FIB pits on this sample already. We'll just go to one of these to start with. The first thing we want to do is find the eucentric height. And I know there was a question about that earlier. The eucentric height is close to 4 millimeter working distance, which is where we're at right now. But you want to specifically find the eucentric height by tilting. The eucentric height is the center of the tilting axis. So the way I find it is I'm going to put a feature right in the center of the screen. So let's just use this fiducial X, put that right in the center. And I'm going to go over here to my tilt control, and I'm going to do a small tilt angle, like 10 degrees. So I'm just going to say 10 degrees and hit enter. And as the stage tilts, you see that X moved up out of the screen. I want to adjust the height of the stage using this slider here for stage Z to either raise or lower the stage slightly to bring that feature back to the center. So if I click in kind of this white area here, it'll move a little bit faster. Or I can click the arrows on the ends and do very small adjustments. So I bring that feature back to the center by only changing the height. So now if I continue to 52 degrees, that feature should stay pretty much in the center of the screen. And this is what we refer to as the eucentric height of the stage. Now I can make further adjustments to the height once it gets to 52. So let's raise it up a few more clicks. Okay. So now that we're at the eucentric height, I should, assuming the alignments on this tool are good, the FIB should be looking at this feature or fairly close to it. So to turn on the FIB, I'm going to click on quad 2, to select this as my active quadrant. I had already set this back to be the ion beam. I'm going to go to beam control, and I'm going to say I have to turn the fib on separate from the SEM because the fib's not even on. So I'm going to say beam on, and that will activate the fib. And then I can choose my voltage for the fib and my beam current that I want to use. And then I can hit pause and I can start scanning. So this is my fib image. You can see it looks a lot like the SEM. I can use the same, let me turn the MUI controls back on. Same MUI controls for the fib as long as I have the fib selected. So I can zoom in. Now you can see that I'm about 10 microns offset between the fib image and the SEM image. And the way we fix that is by using the beam shift adjuster. So if I change my beam shift on the fib, I can align the fib to point exactly at the feature that the SEM is centered on. And this is a useful thing to do when you're trying to observe fib cuts. Okay. So now let's say we want to cut into this. So this sample has all kinds of little transistors in it. We want to cut parallel to these line features on the surface. Hopefully those show up on your view. So what I want to do is I want to rotate the stage so that these are horizontal. A good tool for that is in the stage dropdown. It's called Align Feature, XT Align Feature. I'm going to click on that. I'm going to draw a line parallel to that surface feature, and I'm going to say I want to make that line horizontal, and I say finish. And this will cause the stage to rotate so that our features are now horizontally aligned. So now let's say we want to cut into this surface. So I'm going to go to my fib, make sure my fib image is reasonable, and it is. Let's go to a much higher beam current. Let's go up to, let's say, 9 nanoamps, 9.3 nanoamps. Now the large fib currents, you have to be very careful when you focus because you will sputter away the surface while you're trying to focus. So what I like to do is use the snapshot tool to take pictures, or to use reduced area mode and put the beam somewhere that you don't care about because you will sputter away the surface very quickly. So let's just start imaging with the fib, and I'm going to adjust my focus. And you see there I lost my features already. It kind of destroyed the surface. So as the fib is imaging here, it's sputtering its way down through the layers in this semiconductor device. But I think that's pretty reasonably in focus now. And if I look with my SEM, we can see the damage that I just caused. Right, so I just sputtered away all of that material very quickly. So if we want to make a cut in a specific location, we can go to the patterning tab. We can choose different types of patterns. I'm going to choose a pattern called a regular cross-section, which is designed for making a cross-section cut. I'm going to draw a shape on the screen, and we can set the parameters for this cut. Let's make it cut 10 microns deep. Yeah, let's go. It says it's going to take 1:46 seconds. I don't want to wait that long. So I can either make the cut shallower, or we can go up more beam current. So let's go up in beam current. And as I change my fib beam currents, I need to make sure my focus and astigmatism don't change as well. Okay, so this is going to take 52 seconds. I'll just put it right there, and we can hit the Start Patterning button. Okay, so this is telling me that the beam currents was changing while I made the pattern, so I just say Recalculate and play again. So now the fib is scanning in this square area based on the settings I have over here in the Pattern tab. while it's running, if I go to my SEM and I take a snapshot, I can use the SEM to monitor my progress with my fib cut. So when I use snapshot, it pauses the fib pattern for a second, and it's going to take a picture based on my snapshot settings, and then it'll go back and resume the fib cut. Okay, so that's all done. Let's go back. Let's see what the result is. So if I zoom in here, oh wow, it actually is pretty close to the transistors. So if you're not familiar with looking at these things, these are a series of transistors on top of a silicon, it's like a little silicon mountain or little pyramid of silicon. And then all these structures up here are tungsten contacts and then copper conduction paths. So if I want to get a good image on these, I definitely, normally I would clean this surface up with the fib again, but I'm running out of time here. So I'm going to switch to the high resolution SEM mode, and we can just see what these look like with better resolution. And I'll caution you, these are hard structures to image by SEM unless you do the cross-section cuts very well. And by that I mean lots of cleanup steps, generally low voltage cross-section cleanup. So I'm not expecting to get a really fantastic image out of this, but maybe we can see the gate structure. It's drifting a little bit, but you can kind of see this is the transistor gate. So if you want to see what this actually looks like, you can Google 65 nanometer gate. But this is the gate right here. There's a little gate oxide layer right across here that I can't see by this image. And then there's some like silicon nitride, silicon oxide things kind of wrapped around this. And then these are the tungsten contacts that touch the silicon, and that's your conduction path underneath the gate right here. So this is a 65 nanometer technology, which was maybe circa 2004. So it's kind of an older device. The newer stuff is like 10 nanometer length scale, so it's way smaller than this. So pretty hard to see any of that by SEM. We normally do TEM for that. So anyway, that's a really, really basic intro to the fib. One of the reasons I spend so much time with training with the SEM is that the SEM and the fib operate very similarly. They both use the same control panel and the same user interface. The difference is the fib is a very, very basic microscope. It does not have any alignments to it that the user will do. So you simply choose your voltage, choose your beam current. You will do focus and astigmatism, and that's it. So if you can operate the SEM, you can certainly operate the fib on these tools. When we do training for users for making TEM samples or atom probe samples, we go through the specific sequence of steps for those lift outs and how to make the sample with the fib. But generally, the actual operation of the fib is not critically difficult. So what we're going to do as the last step here is we're going to shut down the tool. So to shut down the tool and take the sample out, we're going to go to beam control, and we're going to turn the beam off. And I have to turn off both beams. So that was the fib, and I click on the SEM quad, and I can say beam off on the SEM as well. So now my beams are off. And then we're going to click vent. Now I have this tool set up that when I hit vent, the stage is going to lower automatically, and it's going to put the tilt back to 0. But that may or may not always be the case. It's a setting that can be changed. So when I hit vent, I just want to make sure that the stage drops. If it doesn't, you would go to the navigation tab and just type in 0 for tilt. and 0 for Z. When I turn the beam off, the Z-axis unlinked from the SEM. So 0 is now down, and you can see that because the positive arrow is up. But if I hit vent and say yes, the tool should lower the stage. There it goes, it's dropping. So then what we'll do is I'll take the samples out of the stage adapter, I'll put them in my own storage once it's vented, and then I'll close the door and hit the pump button and make sure that the chamber is sealed up. We don't have to wait until the chamber gets to high vacuum to leave the room, but make sure at least that the vacuum pump is on and that the chamber is pumping before you sign off and walk away. So it'll just take a few seconds here for the chamber to vent, and then I'll demonstrate taking samples out, and then we will be all done for today. So it looks like there's still a couple of you watching. If you have any questions, you can put them in the chat while we're waiting here. Otherwise, feel free to send us emails or come talk to us in person. I do most of the training for the Helios, but the other staff at MC Squared are also very capable of answering questions about this system. So come talk to any of us if you have any questions. Again, make sure you put on clean gloves. I've had these gloves on for a while. I put on a new pair of gloves over top of these. Carefully open the door. And then loosen the adapter, and I'll take my samples out. Make sure you check with the height gauge. You know, if you adjust the height of the stage adapter, you don't want that to be too tall, because that, even though there's no sample on there, that could run into the lens. So make sure that that's appropriate height. Carefully close the door. Again, we want to be watching the chamber camera as we do this. Make sure we don't hit the lens. And then we hit pump. And then just kind of gently push on the door. Make sure it's sealed up. You can give it a little pull just to double check. All right, and that's it. We're all done. So I'm going to log off the system. And we'll, okay, I got a couple questions here. Jeremy is asking, I've been using FEI Nanolab at Georgia Tech. Should schedule more in-depth training with me. So if you've used FEI dual beams before, I believe that you'll be able to use these tools without more formal training, as long as you've used all the components. So If you've used, so you said a nano lab, I'm guessing that means it was a Helios. So there's also the FEI Nova nano labs as well. But as long as you've used an OmniProbe style manipulator and you've used the gas injectors for doing lift outs, then no, I don't think we need to do specific training over that. I'd be happy to help if you'd like, but I would leave that up to you. But generally for new users with FIB, they don't have any experience with any of the components on the tool, so we normally would do more specific training covering all those components to do the lift out. But we should talk about that maybe offline, either by email or in person, to arrange a specific training for your sample. No, it wasn't a Helios. Okay, so yeah, so the Nova Nanolab, we actually have a Nova Nanolab here. So if you'd like, you can use that one. It'll probably seem very familiar to you. The Helios, this Helios has the same OmniProbe manipulator that your system probably had at Georgia Tech. So you probably don't need a whole lot of training for the lift out procedure from me. But again, I'm always happy to go through those trainings with users. All right, if there's no more questions, I'm gonna go ahead and sign off. I have to hand the tool over to another user here in a couple minutes, so I need to get all the equipment shut down. So I hope to see all of you in the facility again, and thanks for watching.